I would call it the physicist's nightmare. The modern world runs on numbers that don't make sense. We are told that the latest smartphones, the most advanced AI servers, and the military systems guiding global hardware are powered by 4-nanometer chips. But let's strip away the corporate marketing and look at the raw, terrifying physics of that statement. What does 4 nanometers actually mean? A single atom of silicon is roughly 0.2 nanometers wide. That means a 4-nanometer transistor gate is only about 20 atoms across. If you took a single human hair and sliced it lengthwise, you would need to slice it 100,000 times just to get a strand as wide as a single feature on these chips. Let that scale sink into your mind for a moment. We are engineering structures where an error of just 5 or 6 atoms means absolute failure. And here is the absolute mind that the tech industry doesn't want you to think about. How do you measure something that small to verify its quality? How do you run quality control on an atomic grid? Standard manufacturing relies on optical inspection, using specialized cameras, lenses, and light waves to check if a part is made correctly. Whether you are building an electric vehicle engine, a supersonic jet fuselage, or a premium medical device, light is your ultimate source of truth. Cameras look at the components, lasers scan the surfaces, and software calculates the variances based on the light that bounces back into the sensor. But visible light has a wavelength between 400 and 700 nanometers. Trying to use a light wave to measure a 4-nanometer structure is like trying to measure the thickness of a single thread using a standard baseball bat. The tool is physically too fat to see the object. The light wave cannot physically resolve the shape because the feature is smaller than the wave itself. The light simply bends right around it, completely uninterrupted. It is called the diffraction limit, and it is a hard physical wall built into the universe. Yet, if a single transistor is misplaced by the width of 3 atoms, the entire multi-billion-dollar chip fails. A leakage of current occurs, the circuit shorts, or the timing of the entire processor falls out of sync. Welcome to the hidden world of semiconductor metrology and quality assurance. In this masterclass, we are going to look under the hood of the most precise, high-stakes quality control war on Earth. We will uncover the impossible physics, the multi-billion-dollar hardware monopoly, and the raw economic mechanics of how engineers measure what is mathematically invisible. Welcome to Side Entrepreneur. Chapter 2: The Death of Optical Sight. In traditional automotive or aerospace quality control, precision is governed by tolerances you can touch. You use micrometers, laser scanners, and coordinate measuring machines. If you are working in high-precision aerospace, a tolerance of 1/1000th of a millimeter is elite. If your turbine blade or your engine block is accurate to within a single micron, you have achieved world-class manufacturing standards. In semiconductor manufacturing, that level of tolerance makes you a caveman. A micron is 1000 nanometers. In the world of modern advanced foundry nodes, a micron is an ocean of error. When the industry pushed past the 28 nanometer node over a decade ago, optical physics hit a brick wall known as the Abbe Diffraction Limit. Formulated by the physicist Ernst Abbe in 1873, this fundamental law of nature states that you cannot resolve an image of an object that is smaller than half the wavelength of the light you are using to look at it. Even if you use the shortest ultraviolet light wave visible to the human eye, you hit a hard wall at around 200 nanometers. Think about the economic catastrophe this created for quality assurance. A silicon foundry, or fab, costs up to $20 billion to build. Inside these ultra-clean facilities, automated machines are printing billions of transistors onto a single silicon wafer the size of a pizza. If the machine's calibration drifts by just half a nanometer due to thermal expansion, floor vibration, or acoustic resonance, it prints a structural flaw. If you can't see the flaw while it's happening, the automated assembly line will keep printing dead chips for hours or days. A single batch of ruined wafers can cost the company $50 million in a single afternoon. Quality assurance could no longer be passive. It couldn't wait until the chip was completely finished, packaged, and plugged into a computer to test if it worked. If you wait until the end of the manufacturing line to find out your printing machine drifted 48 hours ago, you are already bankrupt. Engineers needed to measure the physical shape, the exact height, and the precise sidewall angles of structures 20 atoms wide in real time, right on the factory floor between every single printing step. To solve this, they had to abandon light entirely. They needed to find something with a wavelength smaller than an atom, and they found it by weaponizing electrons. Chapter 3: Feeling with electrons. Instead of bouncing a fat wave of light off the chip, modern semiconductor QA uses a technique called critical dimension scanning electron microscopy, or CDSEM. Instead of a standard light bulb or a traditional laser emitter, the metrology machine uses an electron gun. It fires a highly concentrated beam of high-energy electrons down at the silicon wafer. Because electrons have a quantum wavelength that is thousands of times smaller than visible light, they don't bend around the 4 nanometer feature. They smash right into it, interacting directly with the atomic landscape. As these electrons strike the silicon structure, they knock secondary electrons out of the atoms on the chip's surface. A highly sensitive detector positioned above the wafer catches these escaping secondary electrons and measures their precise quantity, velocity, and trajectory angle. If the electron beam hits a deep vertical trench, fewer electrons escape back to the detector. If it hits the top of a sharp transistor ridge, a flood of electrons bounces back cleanly. The machine's software then takes that massive stream of raw data and reconstructs a hyper-precise, three-dimensional digital image of the nanometer scale landscape. But even this creates a massive QA crisis. Electrons carry an active electric charge. When you blast a delicate 4 nanometer photoresist pattern with a high energy electron beam just to measure it, you can actually warp, melt, or alter the very structure you're trying to inspect. The energy from the measurement tool itself can destroy the product. It is an industrial version of the observer effect. To get around this, QA engineers had to develop another impossible alternative: atomic force microscopy. Instead of looking at the chip with a beam, they decided to physically feel it. Imagine a needle made of a single diamond, sharpened down until the very tip is exactly 1 atom wide. This needle is attached to a hypersensitive cantilever beam balanced by a microscopic spring system. The machine lowers this needle onto the chip and drags it across the silicon surface. As the single atom tip moves over the 4 nanometer valleys and peaks of the printed transistors, the needle deflects up and down. A precise laser bounces off the mirror-polished back of the needle tip, measuring that movement down to a fraction of an angstrom. 1 angstrom is 0.1 nanometers. It is the ultimate version of Braille, played at the atomic scale. Chapter 4: The Math of Invisible Defects. But here is the catch that breaks the scalability of electron microscopes and atomic needles. They are painfully economically slow. An atomic force microscope has to physically move a needle across the wafer, dragging it atom by atom. A scanning electron microscope has to focus and scan its particle beam pixel by pixel across a massive surface area. If you try to inspect every single one of the trillions of transistors on a single wafer using these physical tools, it would take months to verify a single day of factory output. In mass production, speed is money. The factory must move, the machinery must produce, and the output must be validated in seconds, not weeks. This gridlock forced the birth of the most complex quality control trick ever invented: optical scatterometry. QA engineers realized that while they couldn't get a clean, visible image of a 4 nanometer structure using light due to the diffraction limit, the light still didn't disappear. It still hit the wafer, and it bounced off in a highly specific, scattered distortion pattern. Think of it like throwing a bucket of water at a hidden staircase in a pitch-black room. You cannot see the stairs with your eyes, but by measuring exactly how the water splashes off the steps and hits the floor, you can use advanced fluid mathematics to calculate exactly how high, how wide, and how steep the hidden steps are. In scatterometry, a machine blasts the wafer with a complex, known mixture of multi-wavelength polarized light. The light scatters into a chaotic, messy, unreadable reflection pattern. A high-speed sensor captures this broken light data and feeds it into an advanced industrial supercomputer. The supercomputer does not try to build an image. Instead, it compares that specific scattered light data pattern against a massive, pre-calculated mathematical library containing millions of theoretical chip shapes and defects. When it finds an exact mathematical match in the database, it instantly deduces the physical dimensions of the chip down to 0.1 nanometer precision. It is pure, unadulterated mathematics masquerading as quality control. You aren't seeing the chip, you are calculating its physical existence based on the shape of a shadow. Chapter 5: The Yield Metric Engine. To understand why this matters to a global business, we have to look at the financial foundation of a semiconductor fab. Everything in this industry is governed by a single, ruthless metric: yield. Yield is the percentage of working chips on a silicon wafer compared to the total number of chips printed. In a standard automotive plant or a consumer electronics factory, an acceptable defect rate is measured in parts per million. If an assembly line produces a few defective doors or loose screens, the parts are tossed out, the line is adjusted, and the financial impact is minimal. The process is stable, predictable, and clear. In an advanced semiconductor fab running a brand new 4 nanometer process node, the initial yield rate can be as low as 50%. That means half of everything you produce using $20 billion worth of machinery is literal garbage. It cannot be repaired, it cannot be reworked, and it cannot be sold. It is melted silicon destined for the scrap bin. The entire financial survival of the factory depends on how fast the QA department can use metrology data to find out exactly why those chips are failing, locate the sub-nanometer drift, adjust the tool calibrations, and push that yield rate up to 90%. Let's do the macroeconomics on this. A single modern wafer can hold hundreds of advanced processor chips. Each of those chips might sell for hundreds or even thousands of dollars to an AI data center or a smartphone manufacturer. A 1% increase in manufacturing yield across a premier semiconductor fab can represent an extra $100 to $200 million in pure profit every single quarter. A 1% drop because a machine drifted by the width of 2 atoms can destroy an entire year's corporate guidance. This is why metrology machines are placed after almost every single major step in the cleanroom. The wafer is printed, measured, etched, measured, layered, and measured again. Quality control is not an administrative checkpoint at the end of the line. It is the primary data engine that dictates whether the company makes billions of dollars or collapses under the weight of its own capital expenses. Chapter 6: The Metrology Monopoly and the Macro Gap. This brings us to the ultimate macroeconomic reality of the technology sector and the massive blind spot in the modern tech wars. When you hear about the geopolitical tension between the United States, China, Europe, and Taiwan, the media focuses almost entirely on lithography, the massive, complex machines built by ASML in the Netherlands that use extreme ultraviolet light to print the chips. The narrative is always about who can buy the printer. But printing the chip is only half the battle. If you cannot measure what you print, your $20 billion factory is functionally blind. You are printing garbage at high speed, with no way to know until it is too late. This has created a secondary, highly lucrative monopoly that almost no one talks about. While ASML rules the printing process, a small elite group of companies, such as KLA Corporation, Applied Materials, and Hitachi, completely rule the metrology and QA market. Their systems are the absolute gatekeepers of global tech supply chains. Without their coordinate mapping, their electron scanners, and their scatterometry math libraries, the advanced lithography printers are useless hardware. When you look at global industries through this lens, you stop seeing simple product manufacturing. You begin to see structural bottlenecks. Every time technology pushes a physical limit of science, an immense gap opens up between the companies who can design a concept on a computer screen and the elite few who possess the specialized, data-driven frameworks required to execute, verify, and control the quality of that concept in reality. The lesson of the 4-nanometer chip is simple. Leverage does not belong to those who build loud, massive things. True economic leverage belongs to those who master the microscopic details, establish the systems of continuous verification, and control the metrics of precision. In the modern economy, the crowd is fighting over the flashy, high-level concepts. They are trying to build the loudest products, but the structural money is made in the bottlenecks, in the validation systems, the quality frameworks, and the invisible metrics that keep the entire system from falling apart. If you want to escape the noise of the standard market and scale real, sustainable digital leverage, you have to build your own systems of absolute verification. You have to find the bottlenecks in your market, master the metrics that others find too tedious to measure, and control the quality of execution. Access our exclusive execution frameworks, digital tools, and assets designed to help you decode these market gaps and build high-yield digital assets in the description below. Subscribe to Side Entrepreneur. We'll see you in the next masterclass.